This is node 1. The call is node 2. This is node 3. So this is element 1. This is element 2. And in fact, this is element 3. Okay, what else? What else do we need? Now, we managed to. I don't want to go this far. This is node 1. Sorry, I'm just using my pad is misbehaving a little bit. Good morning. I think our numbers are good. We like to start outright because we have short today. So on our lecture. Thank you for those who have already registered their attendance, as well as those who are still joining. Remember, you can always use the chat section to raise your question as even as I continue with the chat. All right. Let me just project this. Let me make this full screen for ease of but at least you can see it quite clearly the way I'm seeing it on this slide. We are still the topic production finite element. I mean that's our course unit. And we managed to look at two elements so far, the string element, the truss element. So today we are still looking at the truss element, which you call the bar element. But now, they're saying, one that you used last time was like this. So you can consider a scenario whereby we are considering a truss, typical truss. Okay. Let's say you're talking of a truss here. Yeah. Just like that. And we can just have a dream about truss. Okay, we are saying that maybe there is illustration. Okay. The arrow support on the other end. So this is node 1. Let's call this node 2. I think this is node 3. So this is element 1. So this is element 2. And in fact, this is element 3. Okay, what else? What else do we need? Now, we managed to. I don't want to go this far. Sorry, I'm just using my pad is misbehaving a little bit. But I wanted to highlight something here that last time we are looking at, okay, we are looking at this one. One that this is now the axis, what we refer to as the structure orientation. The class is oriented in that direction. So this axis we can define any point, any coordinate using the x and y as shown. So we consider this element 1, whose now this element, when you look at it, this element 1, when you look at it, oriented the same direction. You're talking of this element 1, it's oriented the same direction as now what we define here. Look, this element. But how about element 2? If it's inclined a certain angle here, angle we can refer to as theta. This is the element that we are showing now on your right hand side. That's what we are calling first element in 2D space. Actually, what we are just considering was 1D. That is, we were just considering with one axis. We could define any motion and degree of freedom, any formation towards, of course, formation, whether contraction or elevation. We can define using one coordinate. That is what we in 1D space. Now, it's oriented there. Because now we'll have the component in y and the x axis. So this is what we are referring to as a bind to space. But just as a summary, because I've been mentioning about it, remember we talked about the local and global coordinate system. We say on an element, each element now will be oriented in its own coordinate system at element of scale. Consider element one. Consider this element one. I can just highlight here. Element one, I've got small y, use small letter x and y. Then I've got small y axis, y and x. Okay? Now, when you look at element two, in this one I've got its own orientation, its coordinate on this direction, small x, y, small y. You can see all the elements, even element three will have its own coordinate system. Therefore, when we come now to the assembly stage, we need some, remember we are assembling different stiffness matrices of individual elements, called the element of stiffness matrix, get the global stiffness matrix. And therefore, we need to assemble, and you realize, or you looked at, but assemble is just matrix operation, is addition. To add, we have to add them when they are common on its system. And then that brings us to issue of we refer to as transformation. For elemental stiffness matrices, we have to transform them. Not just stiffness matrices, but any quantity, elemental quantities in local coordinate system have to be transformed to a global coordinate system or to align the structure coordinate system so that you can be able to add them up. Otherwise, you cannot add two things which are different. So, to do this, we need to obtain what is called transformation matrix. Okay? And this is the today's lecture. How do we derive the transformation matrix? To transform from local coordinate system to global coordinate system. So you have noted that we have these notations. From local coordinate system, we use small xy, global capital XY. Local coordinate system, now the use and the use, remember you are just, you have just been introduced to you because we are only concerned with axial deformation along the x-axis. Now, because we are going to have a component in the y coordinate system, I remember the method of resolution of the joint. We're going to have a component. That's why we are now we are saying we are going to have a multiple component. We introduce V. U and V now. No coordinate system, of course, we have one degree of freedom at a node. But a global coordinate system, because now we have U and V, horizontal and vertical displacement. Remember, we are talking now about displacement. The global coordinate system is the displacement at this node. If this structure deforms, in whatever direction, instead of this member, we have a component in the x direction, maybe y direction, depending on where the formation of or the direction that the deformation have taken. Okay. Understand what I mean here is that if for a structure, okay, I think I have to give up this. I have a touchpad here which is helping you. A pen pad, but it's bringing more problems than helping you. Okay. So what I'm saying is, structure, let's say, deforms. Okay. A structure deforms something like that due to application of load. So, and this node we want to the deformation, have the x component, which we are calling U, and maybe the y component, if they are sinking, which we are calling V. And for elements, we are using small letter U and small letter Z. For the global, there's a structure we're using U, E, without that. This for this mark, for U prime, Z prime, and here U. Good. Enough with the notations. Remember, don't forget this again, because we on referring to them. But, for an element, bar element, stiffness matrix is equals to P is equals to A, E over L, A, 1 minus 1 minus 1, 1. Don't forget that. let's see the transformation. We have this. I think I need to for each of drawing. Start. Please. Okay. So if you look at this element, it's the same element that we have, but now I've positioned it here. So what is the, let's first plot the axis. Let's first plot the global coordinate system. So we have that. And we have, of course, now in this direction. Okay. And this one now we have, this is the Y, capital Y. This is the capital X. So we are going to transform all the components into this coordinate system. So let's consider this node. We have two nodes, node 1, which is called node I, and node J. Now at node I, just for the same element, you see it has got its own coordinate system, elemental coordinate system, or coordinate system, small x, this one, and small y, okay? Because the coordinate have to be a right angle. Now, so we are kind of transforming, moving this to get the vertical component and the horizontal component. Now, you can draw, of course, you can complete this angle because we are going to use two things. We are going to use geometry and trigonometry, which is something I know you are familiar with. So what we do here, I can plot, because this line, you are seeing this line here. Okay. This line is parallel to this. I can draw a line parallel to this axis. Okay, here. So I end up having a right angle triangle. So my triangle, this triangle is right angle. Okay. Let me extract it for you so that maybe you can see it a bit clear. So you're saying I have this right angle triangle like this. Okay. This right angle here. Okay. And we are saying this angle is theta. This component, we have it u prime I, okay? And then we have a component, okay? We have a component ui, the global coordinate system. This is the axis capital X, this is the axis capital Y. But I just wanted to extract this triangle for you so that you can see it. So we're using this triangle. We're using this triangle to get the different component. So this is your element here. Don't forget. Okay, this is your element. This one here. We want to get the vertical component of the same and the horizontal component. So when you use this angle theta, before I leave this place, it's also good to know. Okay, let me just finish it at this part. Using this angle theta, you can see this right angle triangle. U prime I is the horizontal, is the, use this. I know you know about this Okator. Okay. Whereby we say sine, cos, and tan. Okay. There's a hypotenuse. So the horizontal or this UI, when you look at this right angle triangle, the way it is, then on the x-axis, when you want to get the component, this is the adjustment to this angle theta. So we can say cos theta equals, cos theta is equals to what? U adjacent of hypotenuse. So U prime I over UI. Therefore, we have the horizontal component of UI, U prime I, which is equals to UI cos theta. So in a similar manner, remember we have a component, the capital VI here. Not the capital, but VI without a line, which of course is here. Can drop that here. We have VI here. Now, when you look at this triangle now again, hope I'm not losing somebody. When you look at this triangle, you have formed another right angle triangle here. And now the right angle is here. So that if you use now the second triangle, you want to get the vertical component, okay, of UI still, the horizontal displacement U prime I. So you see this one now will be U prime I is the hypotenuse. Okay, the hypotenuse, and you want to get opposite, so use sine. So you can say cos theta again is equals to cos opposite, sine theta is equals to opposite, which is VI over hypotenuse. U sorry, something is amiss, somewhere. Something is amiss somewhere. You need not drop that line there. Let me just repeat this. Yeah. Yeah. So sine theta is equals to VI. Sine theta is equals to UI, that is opposite over VI, which is hypotenuse. Are we missing something here? You following? Everybody following me here? Because I'm just trying to get the rectangles, right angle, triangles, sorry, that we can use similar triangles. We started with this triangle, the one now is on screen, and we are able to get the horizontal component, okay, UI. We are able to resolve the U prime I into UI, the horizontal component using the cosine. Now we wanted to get the same, but now the vertical component. Okay, so it's vertical component. Of course, definitely it means to get this vertical component, let me introduce something else here. So if you go back to our triangle here, I bring back my triangle so that I have space for working. So the line that I was drawing here, I could extend it. This line, I plotted a line here. I could extend it to this one. Okay. Yeah. So that when you look at this, we have this was a right angle triangle, and then this is a right angle triangle. Of course, using similarity, okay, if this angle is theta, this angle is 90, then this is angle is 90 minus theta. Okay, then if this angle is 90 minus theta, and of course we know this big angle here is 90, then this angle here is theta. Right? So you have theta, we have this is the vertical VI component, okay, and we have the U prime I here. So you have the U prime I, this one, We have the VI, and of course, I wanted space because now I have extended this line here. I've extended that line there. Okay. So we can be able to get the vertical component here or resolve this UI to this vertical axis by using sine. So you see, we have this. We know this UI and we want VI. So we know the we have the hypotenuse and we know the opposite of this angle theta. Opposite UI is opposite. So that's why we are using sine. So we can say sine theta is equals to opposite, which is U prime I over hypotenuse. Remember, we are using this right angle triangle. We are using this angle on the top, on the upper part of this element. Okay, so this side VI is a hypotenuse. So VI. Therefore, VI or U prime I is equals to VI sine theta. Okay. Now, let's now add them up. I want to add them up. Add them up. So what we are saying is, we are saying that UI U prime I have got two components, which is equals to UI cos theta. So of course now this is this one that I've brought to this side. And now we can bring the other one here, okay? The vertical component. So we are saying again, U prime I is equals to VI sine theta. So you can add this to have overall UI prime is equals to UI cos theta plus VI sin theta. Just hoping we are together so far. Now, the second part, which I would like you to somehow visualize again, is to get now the component of the VI. Remember in this axis here, we have this component, VI prime. Remember, within the linear, we said the linear rate, where we say that our element will only, be formed by axially, that is stretch or compression. For at the element scale, the VI prime is just that it teaches firing. I mean, our truss member is not stretching in that direction. But of course, for the structure, the truss, the formation of the node can be vertically and horizontal. So what you do here, we extend this axis, this direction. So remember this now is negative capital X. And then we can draw the same way we drew this line parallel to this. We can plot another line, okay, parallel to this member. So we plot another line parallel here. This is parallel to this axis. Like we are just taking this axis here. Remember, this one was parallel to the elemental y-axis, one is here. This one is parallel to the elemental x-axis. Okay. So with that, when you do that, and of course you can extend here so that you have right angle here. So the axis, the x and y axis are the one that are making the right angle for the triangles that you want to use. So you're going to use this triangle and this triangle. Okay. Remember, on this direction, now this will become negative UI, because this is UI on this side, but now on the negative side. We have the VI here. Remember, you have VI prime here. So what else do you need? You have, of course, you can now use similarity. If this is theta, this is 90 minus theta. This is 90. This is 90 minus theta. So this is theta. Okay. This being theta, this being 90. This is 90 minus theta. This being 90. Of course, this now being 90 minus theta, and then you take the big triangle here, 90. Then this is theta. So in order to get this angle and this angle, use this triangle and this triangle now to get the vertical component. In similar manner, you are going to get VI prime is equals to VI cos theta on one x-axis, and VI prime is equals to minus UI sin theta on the horizontal scale. And when you match these two, you're going to get VI prime is equals to UI cos theta plus no, we need to correct that. We're going to get minus UI sin theta plus VI cos theta. So it's very simple thing to do to derive. Just have clarity as you are projecting these lines so that they don't confuse you. So I've left this. I'll just move quickly with this one. Because in the interest of time, I don't have ample time, but again, it's something very simple. You can be able to derive that so that I can get to the core of what you want us to do. You know, now you can write this together. Okay, U prime I is equals to UI. Let's start with the let's arrange in terms of UI, VI, UI, VI. Of course, VI is like that. So UI cos theta plus VI sin theta, just putting them together, and therefore, and the V prime I is equals to minus UI sin theta plus VI cos theta. So you can write in matrix form U prime I V prime I. Okay, that's a displacement vector is equals to. So you see this is cos. Let me just see sine minus sine cos. Yeah, and then you have U I V I. In short, we are saying U in local coordinate system. So let's say U prime is equals to this matrix, which can say T tilde, just notation, U in the global coordinate system. If you can read the local coordinate system, the deformation local coordinate system is equals to a transformation matrix multiplied by the global coordinate system. So you can see you have been able to transform. You can be able to transform the local coordinate system, the deformation in local coordinate system to global coordinate system using a transformation matrix. But this transformation matrix is not complete because we just transform this node I. So the same will happen when we come to J. Okay, the same will happen when we come to J. Let me get this space here. So when we come to J, the same thing. Actually, nothing changes, only that now the notation is J instead of I. Okay, so that we are going to have the same equation. Just erasing this. Okay. Now for J, we're going to have U prime J, V prime J, and that is the second node, equals to cos sine minus sine cos uj vj. Hope we are together up to that part. And now what remains, of course, now to describe the whole, to transform the whole element, the two nodes together, we can get, we can match the two equations. We can match for the i's, the two nodes, and the j's, so that you have, of course, remember, at the top here, as I said, for this matrix, when you come to margin, you can kind of say this is a component j, u, uj, vj. Here is a component for ui, vi. Okay. So to merge them, just the same way we are doing. Ui, vi, of course, prime, u prime j, v prime j is equals to, it's just a combination of this matrix. You can use superposition. So of course here at the top you have ui, vi, uj, vj. Now we have the displacement vector ui, vi, uj, vj. Okay, and with that now we can be able to look at common terms. We look for ui, u prime, ui prime, we have cos. On here is j, so they are not sharing the node. So you have cos. When you do this, you're going to have cos sine minus sine cos 0, 0, 0, 0. You're going to have 0, 0, 0, 0. I'm doing this faster because you already now are familiar with this superposition method. Okay. So now I have been able to match the transformation of coordinates at the pole nodes from local to global. So you see, from local, the u primes and the v primes, to global, u and v, using a transformation matrix. So this here is what we are calling a transformation matrix T. Okay, at that point I can clear all this. Then we move to the next. All right. So this is what I'm talking about, equation 1. Okay. I didn't want to project this equation so that you don't now start asking where it's coming from. Now, you can mention two things here. You can always cos the cos theta. These are referred to as directional cosines, if you are aware of that. Okay. The cos theta, the sine thetas are directional cosines. And cos theta, you can use the notation L. Sine theta, you can use the notation M. The directional cosine, of course, where cos theta will be equals to xi, okay? Cos theta will be xj minus xi, okay? Xj minus xi over L, the length of the member. And of course, sine theta, which is equals to M, is equals to yj minus yi over L. So anyway, don't be worried so much about this. You can either use cos C. I've just summarized, just use the small c so that I simplify my writing. So as you can see in this equation, the first component here, we had labeled it as small, t tilde, to represent a part. So our equation here can further be written as, can further write this as, from local coordinate system, remember this is in bold, so this means it's a matrix. Local coordinate system, u prime, we need to multiply the global coordinate system or global coordinate quantities by a transformation matrix T. Now this overall T is composed of the small, the transformation matrix of the node T tilde, T tilde. You can see this component here is the same component here. So this is in compact form. At any quantity now, Any quantity in local coordinate system can be transformed into global coordinate system using that transformation matrix. Okay. So, like if you want to get the force in global coordinate system, you just need to, we have it in local coordinate system at elemental scale. You just need to pre-multiply the global quantity with the transformation matrix. And remember, I know you know this, the order of matrix operation is very important. Okay. This T being here is not the same as the T being after F. Now going forward, you can be able to obtain for the same. Remember, at the local coordinate system, this is just a recap. We had the finite element equation. Elemental finite element equation is equal to E of L, that is K, okay, F. Yeah, this one we know that F is equal to K U. So if you wanted to say K, you could say a local coordinate system. Now you can introduce these prime symbols so that you have F elemental. That's what now you have. You just put in this. This one is what you have in your previous class, but now we are introducing this prime choice in the local coordinate system. Because what remains is to get the stiffness matrix transformation or transform stiffness matrix for the whole structure. Okay? So this equation, when you see argument, it means you can you expand it to include zeros. Argumenting this equation, what we are just saying is that this equation, the one at the top here, just had the U and the V. UI, UJ. But now we have brought about, because of the nature of the orientation of our member, we have the vertex of each component. That's the one that we are introducing. So we are going to just argument it, expand it, UI, okay, UJ, UI, VI, UJ, VJ, okay? Because of course you can see this element, UI, VI, VJ, VJ. As you can see, we say there is no force. For this member, there is no force acting on this node like this direction, okay? So at the elemental scale, these things don't make any sense. But at global scale, of course, you're going to have this force component. That's why you are finding this one being 0, Fj. This Fy, I want to have Fi and Fj because the force is on this direction. We do not have force in the vertical direction. So this is 0, this is 0. And then, of course, you can see all these columns, rows and columns are 0. The ones associated with Vi and Vj. But you are doing this so that you can be able to do summation, as you are going to see slightly ahead. So this is what I was saying. You can write now, our equation can be written as K prime U prime of F is equal to Ku. This is our finite element equation. So in local coordinate system, remember to include this prime symbols. So using transformation given in equation 2 and 3. Remember in equation 2 and 3, we said any quantity, that is F and U, can be transformed into global coordinate system by pre-multiplying the global quantity with the stiffness matrix. So remember we said F is equals to T times F. You see, this F here is equals to this part. This was equation 3. Now, U, we already derived it. We spent a lot of time deriving that. U is equals to pre-multiplication by transformation matrix, U. Okay? And then, of course, our K. This is the K we want to know. This is the K. Or we want to know how to move from local coordinate system to local coordinate system for the stiffness matrix. Now, looking at this equation, okay, looking at that equation, we can be able to pre-multiply. Look at our equation here. Yeah. F is equals to Ku. In global coordinate system, of course, already we have the F and we have the U. If you remove this T, everything comes on this side, you have the equation for global coordinate system. And what you do, we can multiply. One thing that you have to note with this matrix, one of the characteristics which we are utilizing from this matrix is that the matrix T is this matrix T, if you look at it, it's orthogonal. Okay? The matrix T is orthogonal. And orthogonal matrices meaning they are transpose. If a matrix is orthogonal, we are saying the transpose of that matrix is the same as its inverse. Matrix operation, for those who really take time to look at it. So the transpose, when we say a matrix is orthogonal, we say its transpose is just the same as its inverse. So once you understand that a matrix is orthogonal, then you don't have to determine to get the inverse, you just need to transpose. And transposing is easier because we exchange the rows value with the column values, we interchange them. Now utilizing that fact, we are utilizing that so that you could be able to move quickly here. So what we are saying is the same. Remember, to remove the T from this side, we needed to pre-multiply with the inverse. You know, if a matrix multiplied by inverse, you are left with identity matrix. Identity matrix, of course, in matrix world is like 1. So we want to be left with 1 here, just an F on this side. Okay? And therefore, we wanted to get the inverse of this matrix T. Now, using that advantage, and utilizing that advantage that T is orthogonal, now you can just get the inverse by getting the transpose. Okay? So T transpose, you multiply both sides by T transpose. On this side, you are left with identity matrix I, which is equal to 1. Okay? And on this side now, you can see it's T transpose. We have brought it on this side. Order is key. Order is key, right? Order is very important. Remember, this one, if order was not important, we could say, why don't you take this T transpose times this T to get identity matrix I? But see, we have K prime on this part. Okay? Elemental stiffness matrix on this part. It's coming in between. So our operation will be first operate the first one, the first two matrices, the resultant matrix that you get, then you do the operation, the T, then whatever you get, you go ahead like that. So order is key in matrix operations. Now, with this, remember the nature or the form of our equation, global finite element equation, or even elemental finite element equation. We say F is equal to KU. So F is equal to KU. We have this U. So everything else here is a capital A. Yeah? For your understanding, you're saying F is equal to KU. This is the U. This is the F here. So all this is K. And therefore, the elemental stiffness matrix global coordinate system K is equal to T transpose K prime T. And that's now you've been able to transform or to obtain the global stiffness matrix from Moko to stiffness matrix. So anytime we have a structure having different elements oriented different coordinate system, you first determine the elemental in their elemental coordinate system or the local coordinate system. First, you determine the matrix in that orientation. But now when you come to the assembly stage, to get the overall stiffness matrix, you have to first do this operation. You first have to transform the element to get the same equivalent at the global or in the global coordinate system. What happens when you multiply this? Again, some food for thought and also some practice work. Remember, you have T is equals to, don't forget some of these very simple equation. T is equals to L, M, minus M, L, okay? 0, 0, 0, 0, 0, 0, 0, 0, L, M, minus M, L. So that is T, okay? What else do you have, K? K in the local system, we have it as A, E over L, right? 1 minus 1. Now, for you to be able to operate this, that's why you include the zeros. So 1 minus 1, no, you have 0. Then you have 0, 0, 0, 0. Okay. then you'd be minus 1, 0, 1, 0, and then the bottom one 0, 0, 0, 0. They look like binary numbers. So you have this, you have this. Of course, from T you can get the transpose because you just need to interchange these rows, they become columns. Every row become a column, the column members become rows. And then you do this multiplication, which again, that's matrix of operations, which I don't intend to go into that direction. So what I'm just going to give you is the overall equation. Once you do this operation of multiplication, this is now what you're looking for, the transformed or the global stiffness matrix. Okay, K is equal to E for L, and then all this. And looking at this, of course, we are not called to memorize, but there are things which are very simple that you don't have to be given in an exam setup. Because you see, this thing is repeating itself. This with positives comes this part. Then what you just need main diagonal, they are positive, the same thing. And then minor diagonal, they are negatives. And that's the equation that we use to obtain or to transform from local coordinate system to global coordinate system. Of course, now from that point, everything else now goes. The same procedure that we have been following once we assemble the stiffness matrix, you just proceed the same manner. You introduce the boundary conditions, you solve the equations, then to obtain the unknown quantities, information, maybe forces, and then you can also start recovering derived quantities like the stresses. And in a similar manner, in this slide, I just want to highlight what we already derived from the previous class. The elemental stiffness matrix using strain displacement matrix today. Okay, stress is equal to Young's modulus times strain. The Young's modulus, we're able to express it in terms of displacement vector and displacement strain displacement matrix. And in this format, you expound it. It's very simple to obtain that, or in compressed format. This is it. Okay. What have happened here? We have just taken use because in terms of stress for elemental, we are talking of elements, not the global element. There is no stress that will occur in the y coordinates. Okay, the y, small y. That's why you see we are just concerned with u, I, and u, j, the u components, the axial components. So don't ask yourself why have our matrix condensed. It's still our matrix that we are using. The transformation matrix, if I take you back to it, still our transformation matrix. Okay, our transformation matrix that we derived there, but we are removing this component, the v's. So we are removing the second row and the second column. I mean the second row and the fourth row, the ones associated with v's. Okay, that's why you are seeing LM 00 and 00 LM. Good. Well, derivation may seem scary, but when you come to application, it's quite simple. And you can do so now by looking at a simple example. Let me first see whether there is any question. It seems that most of you are together with me. I don't know whether you'll be able to finish this question because we only have about 8 minutes, but we need to do this one to enable you to understand or to appreciate what you have just derived. Don't want it to evaporate. So you're given a simple truss, very simple plain truss made of 2 bars. I'm moving ahead because I can see no question raised so far. So good. And you're given the material properties E, the geometry A and L. There's a load applied at node 2, node P1 and P2, horizontal and vertical. You are required to determine displacement at node 2. And of course, stress in each of the bands. Okay, let's go straight ahead with this. What you need to have here or to know, of course, this one should never get out of your mind, that this is for element of stiffness matrix, this is EA of L, 1 minus 1 minus 1, 1. Okay? That's always like that. It doesn't change. Then remember the stiffness matrix. We needed to get the stiffness matrix. The global stiffness matrix. This is local. Okay, blank. So you don't need to go through the derivation process. You just know that at the global coordinate system, okay, you know, at the global coordinate system, K is equals to EA of L. Okay, you know, K, the global coordinate system is equals to EA over L, L squared, LM, LM, M squared. So once you just know that, the rest is the main diagonal are the same, the minor diagonal negative. So we can start with the main diagonal, finish this two, minus L squared minus LM minus LM minus M squared. Okay, minus L squared minus LM minus LM minus M squared, and then of course main diagonal, yeah, of course this L squared LM LM M squared. Yeah, this is the equation that we need to use to obtain the global. So K1 global, K2 global. So what are these L's? Remember, L is equal to cos theta. M is equal to sin theta. Okay. Okay, you have the angle 45. The angle 45. So here is expressed in sans. All right. Because now you start punching calculator. You know, it's good to be smart in your work. These are some of the things that you studied maybe in geometry, okay, either in high school or in first year. If you start, you know, if you just get this value, cos theta in your calculator, and then you get it decimal form, you have a lot of calculation, and you have numbers, keep working with large decimal places and all that. So instead of that, now we opt to use special triangle. The isosceles and equilateral triangle. Cos theta is given as √2/2. And sin theta the same. Now, how do we get these angles? You see this, you remember this unit circle? Something called, you are saying cast. Okay? I don't know how you used to remember this, but all angles are positive here, sines are positive, tans are positive here, in the third quadrant, and only cosines are positive in the fourth quadrant. Then, this being the horizontal x-axis, we measure our angles counterclockwise. Yeah. So this is nothing new. It's just something that you know, something basic. Now, then number two, we measure our angles from node I. We leave node I to node J, where I is less than J. I is the smaller node. So if you're talking of element with node 1, 2, or with node 5, 6, you can't start reading your angle from node 6 coming to 5. Look at this. We have node 1, node 2, this is element 1. So we read from this node, this is the orientation. So we know this is the orientation of our member. And this is the x-axis for that member. And this is the y-axis for this element or member. Now, from the horizontal x-axis, angle is 45. Similarly, when you come to element 2, okay, you're given this angle is 45. But element 2, the row node is 2 to 3. So we read the angle from this one, and then we are going to read it from the horizontal x-axis. So this is the angle that tells us the orientation, because we are reading from 2 to 3, from lower to higher. So this angle is, of course, this being 45, this is 45, this is 90, this is 145. So theta 2 is 145 degrees. So always note that. Otherwise, if you read the opposite, of course, you are going to get the same, maybe the same values, but sign, the sign may change if you don't read properly, you don't follow that procedure. Okay, so what do we do? Now, we know L for element 1, L and M is equal to 2/2. So you are just multiplying here. Root 2/2. Even then, this tells you if the quantities are the same, L and M, cos and sine, even LM is like a square of the same. So it seems all these are squares. Okay. If we square this, so like if you say L squared, this will be 2/4. Okay, or it will be a half. So this tells you that all these quantities, they are a half. Therefore, we can move the 2 outside so that we have only 1 inside. Okay, it's like you are going to have K is equal to E. What is E? We are told that E and A remains. L, and then you can move 2 outside. Then this one just becomes 1. Because a half here now, the only 1. We just factored out 2 here. So you're going to have 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, minus 1, minus 1, minus 1, minus 1, 1, 1, 1, 1, as the stiffness matrix for element 1. So you can see application is very easy. Very easy indeed. Only that what you have to be careful with this, the sign convention, how you read the angles. Let's do the same for element 2. Can do the same for element 2. Okay, we have done for element 1. So for element 2, theta is 135 degrees. We have agreed this. We have agreed that we are reading from at node 2 from the horizontal x-axis. So this 135. Okay. So it doesn't matter if this element 1, the node 1 was here, this was node 1 and this node 2, we would have started at node 1. This is the horizontal x-axis, and then we read all the way like this, because we began from node 1 to 2. That's the sign convention. Okay. Then with cos 135, of course, you know this is a complementary angle of 45. You can use cast or you can use your triangle. You can use the unit circle or you can use your calculator. This tells you that in this second, because we know cos 135 is on this quote and the second, only signs are positive. So it means only M will be positive. Cos, which is L, will be negative. Again, remember from our matrix, cos and sine for 45, they are the same. So it means L squared and LM, all these are squares. Again, you square. So that now to express K2, you have whether you square, whether you multiply L times M, it's all the same thing because the quantities are the same, only the signs now change. Now here is where you have to be very careful about the signs. Because we have the signs where you take you back. I can take you back, okay, no need to take you back there, because we can still have it here. We can still have it here. Yeah. I still have it here. Let me just erase this part here. Yeah, no problem. It's not working. K is equal to L squared LM minus F. So you have the negatives, you have the negative signs in the matrix itself, and now we have this negative sign here. Okay. So be very careful when you are doing the pre-multiplication. When you do the pre-multiplication, of course, again, we can factor in. If you square this, you're going to get this as halves. You can factor out the 2. So in the same manner, you're going to get EA over 2L. Then The others because of the sign. 1, M is the minus. Okay. 1, minus 1, 1, minus 1, 1, 1, minus 1. So become minus 1, 1, 1, minus 1, 1, minus 1, minus 1, 1. Okay. So far, so good. Okay. Going forward. Going forward. So this is it. Okay, to remember the U's and the V's, I said you put them here to assist you. Now, we have K1 and K2 in global coordinate system. What remains is just to assemble the same way we did with other matrices. So, if you have done enough practice now, you should see this as something very easy to do to obtain this matrix. Because you just need to add K1 and K2 to get this equation, this matrix here. Get the overall, get this. So you see, why we are able to add? Before, we could not be able to add the different matrices because the two elements are oriented in different coordinate systems. But now, once we have been able to transform them into global coordinate system, now we can go ahead and do the summation of the two matrices. From here now, things become very easy. Now, I can start appreciating why I was saying that this method requires us to employ computers because just two elements oriented in different coordinate systems. Yeah, look at this. And we have not even considered the 3D, which is the reality, actually. You write things are in 3D. So we could be talking about space trans. But here we're just talking about plane trans. X and Y. Again, it have just two members with 3 nodes. In each of the nodes, there are 6 degrees of freedom. That's why you see now we have a 6 by 6 matrix. You can imagine for a typical transit that you have been solving by other methods like the solving of joints. How many nodes we have, degrees of freedom, what will be the size of our matrix? And now operating on these matrices becomes rather tedious. That's why we need now to utilize the softwares. But now with this understanding, as I said, we use simple examples to understand the concept. Whatever now will be happening when you are utilizing the softwares, the abacus, and I hope a number of you have downloaded that, or all of you have downloaded and installed in your computers, because you'll be using it, you'll be utilizing it very soon. You could be doing practice on the same with the solved examples that are given there. And for our assignment 1, remember the first part you could have done the first day. The second part now you can do after today, because we have been able to see how to solve for a trans element using the finite element method. Now the third part now will involve, with the same assignment, will involve now you using the software to solve the same twist problem. And this is just a trans. Okay. Now, once you reach this stage, you have the global finite element equation. Nothing much now remains here. Just follow the procedures that we are following. Bring in the boundary conditions, reduce your equations, solve for the unknowns, nodal unknowns, and any other derived quantity that is required. So what do you know so far about the boundary condition? We want to define the boundary value problem. This node is fixed. Node 3, node 1 is fixed. So you look at these quantities. At node 1, you have UI, VI. You have UI in that direction, VI. These are zeros. So UI, U1, V1, U3, V3 is equal to 0. What else is known? Forces are given. P2, P1. P1 is F1 in the direction X. F1 in the direction X. No, sorry, there is F2. This is not 2. F2 in direction X. P2 is equal to F2 in direction Y. So substitute those known values in this equation. Okay, this is what I'm saying, the boundary conditions, these are known. And some forces, applied forces are known. So you go ahead. If we put 0, this becomes 0 here. You know this is 0, this is 0, 0, 0. What does this tell you? You can remove the rows and the columns associated with 0 degrees of freedom. So you can remove this first row, second row, fifth row, sixth row. In a similar manner, you can remove the first column, second column, fifth column, sixth column. What are you left with here? Some very simple thing. This time. This time. And you see our equation now by just employing the boundary conditions. Our equation simplifies. Okay, to this. E over 12, 2002, and all that. So you can solve this now. Yeah, this is just a simultaneous equation in 2 and U2 and E2. Using the first equation, you can solve for U2. The second equation, you can solve for E2. In fact, these are not simultaneous equations, they are just they are not simultaneous because the first equation I've got only one and how. Okay, we can say they are simultaneous, but the second quantity for the first equation is 0. 0 times V2 is 0. Okay. So in a similar manner, the first quantity, yeah, the U2, the second quantity is 0. Okay. So very simple. You solve that, you're able to obtain what is used and this. Now you can use the equation that we derived in equation 7 for stresses using strain distribution matrix. It was given as follows. Okay. Sigma 1 is equal to E over R. So what is that equation that we are employing? Did you forget this equation? No, this one. This is equation number 7, which you have in your notes, I believe. Okay. So you just need to substitute this direction of signs. The M's, the M's, the LM. Taking note of the signs. You just substitute that. You have derived U. When you come, let's say, you have 2 elements. U1, element 1, element 2. So this I for element 1 will be U1, U1, and U2, U2. This is what now we are doing in this. This is what we are doing in this slide. Just substituting this direction for signs. -1, -1, 1, 1, Lm to get stress in bar 1 is equal to √2 over 2a P1 plus P2. And in bar 2 is equal to the value is given. All right. I think that's enough for now. Because what it means now is to attempt this question. This example, the second one, is similar to what we have just covered using the same principles, only that now we have something we say multi-point constraints. It's constrained in different points. And again, remember you said the finite element method, one of the advantages is that it can be able to solve complicated boundary condition. Okay? So you can see node 3, in this particular case, the orientation. Yeah? You can see how the boundary condition is oriented. If this was to move, because this aurora support, if this was to move, you see it's moving in this direction. Okay. If this was to move, this move in this direction. You see these are a little bit complicated boundaries. Right? But first things first, you don't have to worry about that because that's about the boundary. At this point, we say boundary condition on any quantity, whether it's force. Remember, boundary brings about, they define the displacement and they also bring about the reactions. Now, the first thing that you need to do is get the global finite element equation. And to do so, you need to get the global stiffness matrix for this structure. This is a question. Now, the value of the rod applied at P is given. The length L here is given as 1. Remember, with this angle 45 and this being rectangle, of course, you can get the length of all the other angles. The Young's modulus is given at 10 GPa. This is steel. This is the typical Young's modulus for mild steel. Okay. Then the area for element 1 and 2 is the same. to this element 1 and 2. Remember, another thing you have to notice that um, for this example, we already have discretized our structure. So that's why you see the nodes are defined for you, the elements are indicated. But I mean, if you had solved this, I'd be told to solve using the matrix method of structure, which is the same as the finite element method. You don't have to have these elements shown or indicated. It's you to decide using the criteria that we say how you locate nodes. It's you to define the node locations, and of course now decide which the naming of your nodes and the element. Okay. Now the A for element 3 is also given. It's different from the others. So you are required to determine the displacement of reactions. So displacement. So even looking at the support, if you look at support 1, it's pinned. And this being a pin joint, of course, we do not allow rotation to occur. Okay. Because no moments are going to develop. So use and V's and node 1 is close to 0. Now, looking at the supports 2, being a roller support, you can have a vertical component and a horizontal component. So V at node 2 is equals to 0. Okay. These are things that you do by observation. V at node 2 is equals to 0. But U, because of the roller support, is a constant dynamic. Now, the interesting one is node 3. Node 3, we can only say with confidence that V climb 3. V at all coordinate system is equal to 0. Because the V at the global coordinate system is the one vertically up. And the V at the global coordinate system, V3, is that direction. So if this roller support, as a result of this applied load, we expect to have a movement upwards. As the support moves upwards, we are going to have a component displacement. V3 global is not equal to 0. Only this support will not lift from this, it's a roller. So this support will not lift from this place. So that's why we are saying V3 prime is equal to 0. And this is a fact that you're going to utilize it on. You see how we can be able to transform from local coordinate system to global coordinate system of what we know. This is a known condition. Now, simply put, first we determine the stiffness matrix, but at this stage now, it's something rather easy for you. First, you need to determine the orientation of each of the elements. So element 1, from the vertical coordinate system, this one is 90. Okay. Element 2, this one, so 2, 3, horizontal, the angle theta is equal to 0. And element 3, so we move from the lower node 1 to the higher node 3. So theta is equal to 45. So with that, we just need to take our equation, the equation for the stiffness matrix, global stiffness matrix, and we plug in the direction cosines, and we come up with those stiffness matrix for each of the elements, which is something that I found quite easy for you to attempt. Okay. Maybe what I can do here before I just get this stage is to put it for you, just for the sake of your understanding. I can jot it down. So that we are saying for element 1, theta is equal to 90. And we could put this down if you want. So 90, we know cos 90 is equal to 0, sin 90 is equal to 1. So L is equal to M is 1. Remember our equation, K, stiffness matrix, is equal to EA over L. This is something by now it should be at your fingertips. L squared, LM, M squared. You just need to know that. The rest is minor diagonal negative. Okay. minor diagonal negative, minus ln, m squared. And then main diagonal goes to l squared, lm, m squared. So once you have this, all that now remains is to substitute. So for element 1, we have that. So all these L's, where there is L, because you know there is 0, that one perhaps is to 0. Anything multiplied by 0, 0. So this one becomes 0, 0, 0, 0. Okay? So here you can comfortably say K1 is equals to EA over L. So you can say E1, A1 over L1. Yeah. This becomes 0, 0. And maybe at this stage, we can even factor in these values of E's and A's. I don't think it's much of a hassle now because you already given what are these. Okay. The top row all contains L's. So it is 0, 0, 1 squared is 1, 0 minus 1, 0, 0, 0, 0, 0 minus 1, 0, 1. Okay. So of course you can factor in what are E's, what are A's for 1. Same case, we come to element 2. Theta is equal to 0 degrees. L is equal to 1. L is equal to 0. Remember, cos 0 is equal to 1. Again, you do the same that you have done to the element, you're going to get K2. So for K2, let's substitute the values. We have E2, we know 210, 10 to the power 9. We are putting them to the same unit. Instead of gigapascals, we just talk of Newton per millimeter. Then A, we are given what is A. But as I always say, be very careful when you substitute these values so that they don't increase your working. So where we have, remember this M is equal to 0, sin 0 is 0. So where you have M anywhere, it becomes 0. Okay. These are just operations, matrix operations. Okay. Minus 1, 0, 1, 0, 0, 0, 0, 0. So similarly for element 3, this one you need to determine the L. Of course, you can use theta is equal to 45. So L is equal to 1 over root 2. M is equal to 1 over root 2. Right? And you can use this angle 45 to get the line. Okay. So K3, when you do that, it will be equals to your E A over L. So this will be 6 root 2 times 10 to the power minus 4 of root 2. This comes to how much? Well, this one is a bit tedious. 0.5, 0.5, 0.5, 0.5. Remember, this one I'm giving you in the simplified form. To get there, maybe you may need to do some few steps. It's minus. It is minus 0.5. So I could have factored out even half. Yeah, to half 1, 1 minus 1, 1 like that. Yeah. For some reasons, that won't be done. So it means you can go further and simplify these. Right. So you have it. You have the 3 equations. Yeah. What you need to be careful and note is that when you come to solution, know that this is which node? U1, V1, U3, V3. Those are not to I and J. For element 2, this is U2, V2, U3, V3. For element 1, this is U1, V1, U2, V2. Because why are you writing this here? When you come to superposition, you have to be very careful. You don't add elements which are not at the interconnected node. Because you are going to add U1, U1 with U1, U1 in either of these elements. Okay? You don't want to make that mistake. So what that remains now is just to assemble the matrix, the stiffness matrix. Quite some work here, which again, I can leave it to you at this stage. Sorry, something is happening in my computer. Sorry. Sorry, something not right. This one, which one? Here. When I'm not using my attachment, since the other things cannot be erased. Say clear drawings, now it's done. Okay. Sometimes this technology is weird. Okay, no problem. Even if it's override. So I wanted to project now our equation. Hope you can see it. Yeah? So our equation this now as a result of this is as a result of utilizing, superimposing the matrix. I wish this one could make this clear. If you can't, then I can first exit. Because I don't want to lose any one of you. Allow me to exit the same way I do exit. Because this to exit, you have to go to the end of the slides. Yeah. Then I come back. So you have derived our equations. Our stiffness matrices. Once you superimpose, this is what you're going to get. So that's quite some serious task that you need to use your calculator to punch those figures in. Now, one of the things that you have to notice is that our stiffness matrix, as we always say, they are symmetrical. So the quantities in, if you take the main diagonal, the quantities above the main diagonal are the same. So in this case, we have replaced that characteristic, and then we have just written the quantities on one diagonal and then symmetry. But for a student, I don't want to be this lazy. I mean, if you can be able to try it in full. But with practice, after practice, having enough practice. Because what if this one shows you are confident because you have to come on the top part. What if there's an error in the top part? And then when you're punching the numbers in the bottom part, you realize there was an error. You're going to check yourself again. But if you are so overconfident, you're just going to utilize this symmetric condition. You might not be able to check. So let's be writing in full until we have done enough practice. Good. So apply boundary conditions. These ones are outright. The ones I was explaining at the beginning of this question. U at node 1, U and V, and node 1, U and V, and node 2, V2, and at node 3, V prime, 3 is equal to 0. Again, we know F2x in this direction x is equal to B. And of course, we know as a result of rotor support, there is no reaction that can develop in this direction, the axial direction. So that's why F3 prime is equal to 0. Okay? So you see in our equation here, you do not have the rubber coordinates because this is a group of finite element equation. So how do we utilize this condition that we have here to help us reduce our equation and enable us to solve? Remember, the purpose is why we are given this is to fully define the boundary value problem and to enable us to solve the equation. The boundary conditions help us to even constrain. Remember, initially for the spring element when we started with the first derivation, there was a case we said that there is a singularity. And until we define the boundary conditions, we might not be able to solve. Because in reality, what we are saying is that our structure is floating in space, what we call rigid body motion. Right? Now, with that in mind, so I mean you have to note here, we go back to the elemental scale because we want to transform from element to global. This is the equation we started at the elemental scale. Okay? How we say it to transform one node. One node is the first derivation from local to global. This is what we write as the equation. And this matrix is one that we are saying is T tilde. This one that we stored T, they are signed here. Simple. So we are going to trace this equation because we have another quantity, nodal elemental quantity. We have nodal elemental quantities, not global. Okay, these are the ones that we want to transform from local to global. So utilizing the V3, we go to node 3. So you're saying U3 V3 prime is equal to this, then U3 V3. So the equation that uses V3 is this one. So this is V3, this is 3, where you have I put 3, 3, 3. And therefore, we can use the second equation, which reads, this one reads, V prime 3 is equal to minus M L U3 V3. Okay. This is it. Minus ML U3 V3. Or in simple terms, like that, which we can simplify further to have U3 minus V3 is equal to 0, or U3 is equal to V3. You see, we have gotten a condition. Some known condition. U3 is equal to V3. Okay. In a similar manner, again, we can go ahead and do the same for F3. Okay, using the same equation. Because we said any quantity in our coordinate system can be transformed using the transformation matrix to global coordinate system. Okay. So for F3 again is the same. Okay. So the same equation that we're using for U, we could say F prime I, F prime F in the direction. So this one, if you say F prime I in X direction, so F prime Xi, F prime Yi is equal to this, then F U represent X direction, V is Y direction. Okay. So in short, if I was to write this would be F prime in the X direction, node 3. This will be F prime in Y direction, node 3. This will be F, now in global coordinate system, in node 3. In X direction, node 3. Let me not interchange the name. So you're saying it's F in node 3 in X direction, F in node 3 in Y direction. What are you given? It's X in node 3 in X direction. We are given the top row. So use the top row to get the equation that relates the local quantity to global quantity. So you're going to have F3x prime, F prime 3x equals to Lm U3, V3. And this is what is here. Yeah, this is what we are doing here. F3 X prime, LM F3, okay, 3 is equals to this. Again, we have been able to obtain a condition. F3x plus F3y is equals to 0. So we can apply the boundary condition in the structure. How? If you apply the boundary condition, U1, V1, and V2. Okay? U1, V1, and V2. So we can remove those rows, the first, second, and the fourth row. The first, second, and the fourth column. We can remove them. Okay? So we can remove them. And then we also employ the conditions. You see, we didn't know this, F3, but we can be able to utilize this equation and know F3x is equal to minus F3y. Then U3, we have also seen that from this condition, we have been able to derive that U3 is equal to V3. So these conditions help you to further simplify your equation. Okay. By just substituting the values, U3, and then V3 is the U3. P, F3x, F3y is equal to minus F3x. So you see how it simplifies your work, right? And your equation, you can be able to solve. Now you no longer have 3 unknowns. 3 unknowns, you just have 2 unknowns. And this is what we condensed here. And doing so, you can be able to solve for F3s and the forces and the reactions. I've shown that. So everything can be solved in very simple terms using those conditions. So you can see how you can utilize the information given. The question should be, the information I'm given, can I be able to solve? You realize that if, for example, you did not utilize that, you end up having, you did not utilize this, even, local coordinate system, the given known node of quantities, local coordinate system. If you don't utilize them, then you would end up having equation in 3 unknown difficulty. So they have helped us simplify our equation. So I'd like to stop here for today. And also I know that I've given you more than enough to digest for today. So leave it at that point so that you can do practice and practice on the same. And there are a number of questions, of course, you can get from the 2 textbooks that I give to you. Make sure the class step, I hope you have shared that. Make sure you try those textbooks to get more work examples. I mean, there are so many textbooks and a lot of literature on the same, this finite element methods, this introduction. Okay? So you try that to do practice like this. So any question before we can leave it? My other meeting already is started. So I don't know whether there's any concern, not even any other. Today we didn't have any question. I don't know whether the content was too conc or it was too easy. Usually I get questions, 1 or 2 questions, yeah, and then the other one by the room live question. Today I'm not going to share that live question, live link. Remember, any question that comes up in the course of your practice, you can always ask us in the subsequent question that you can try to attend them. Yeah. Okay. Thank you. That being the case, if there's no question, we stop it at that. So we meet again next week, and thank you for joining on time. Utilize the resources that you have in this platform, the number of resources that you can utilize in your practice. So many solved examples. So you're not here by chance, you're here with a reason. All right, that's all for today. Next week we move to the beam element, but not before you have done enough practice on this. And also you may have to agree when next you need to have first CAD. That's all. I stop this record.